My name is Najwan Nolan bin Cassius and my metric number is BI241100403 and the course name is Computer Architecture and Organization. This is the explanation for assignment 2. Okay, for question 1, part A, we are working with 10-bit words, right? Each bit is placed in a specific position from 1 to 10. Based on the Hamming code rules, check bits are placed at position 1, 2, 4, and 8. These are labeled as C1, C2, C4, and C8 in the table. The rest position 3, 5, 6, 7, 8, and 10 are the data bits labeled D1 to D6. The value row shows the actual bit values from the memory word. For example, C1 is 1, D1 is 0, D2 is 1, and so on. Using this table helps us clearly see which bit we need to use to calculate the check bit and which one are the actual data we want to recover. Here I use XOR to recalculate each check bit. For example, check bit 1 adds up value at position 1, 3, 5, 7, and 9 using XOR logic. The new result is 0, 0, 1. I compare the original and new check bits using XOR to get the syndrome. The binary result in 0010, which is 2, so the bit error is at position 2. We then corrected the error by flipping bit 2 from 0 to 1. After fixing the error, I removed all the check bits. The 6-bit original data is now 011001. Now for part B, we repeat the same steps. The syndromes here tells us that there's an error at position 1. We flip the bits and correct the data word. Removing check bits, we got the corrected original 6-bit data, which is 010101. Okay, let's take a look at question 2, part A. We are multiplying negative 12 times 4 using 5-bit binary. Let's take a look at our initial values. Multiplicand is negative 12, which the binary is 10100. The multiplier is 4. The binary for 4 is 00100. A, the accumulator is 00000, and the Q minus 1 is 0. Let us perform the first cycle. The first cycle, there's no operation. And then the second cycle, there's no operation either. For the third cycle, we'll do A equals to A negative M. Then for the fourth cycle, we do A equals to A plus M. And for the last cycle, there's no operation needed, and the aftershift value for A is 11110, for Q is 10000, Q negative 1 equals to 0. And when we combine them together, it'll become 1111000000. In decimal, it is negative 48. Question 2, part B. The question wants us to multiply 15 times negative 8 in 6-bit binaries. As usual, we put the initial values on, and let's take a look at the first cycle. The operation for the first cycle is A equals to A minus M, and then we shift it. And for cycle 2 to 4, there's no operation needed. We just need to shift it 3 times. And for cycle 5, the operation is A equals to A plus M, and then we shift it as usual. For cycle 6, there's no operation needed. We just need to shift it. And then the final, we combine the A and Q, we got 111100010000, which is in decimal, it is negative 120. This is question 3, part A. where we divided 7 by 4 using the restoring division algorithm. The dividend is 7, which is 0, 1, 1, 1 in binary. The divisor is 4, which is 0, 1, 0, 0 in binary. Then the second complement of the divisor in M, which is 1, 1, 0, 0. The A register is initialized to 0, 0, 0, 0. The first step, first we perform a left shift on the combined AQ register. The result is 0, 0, 0, 0, 1, 1, 1, 0. Then we subtract M from A, which will get the result is a negative. Since the result is a negative, we restore A to its previous value and set Q0 to 0. Step 2, we shift left again. AQ becomes 0, 0, 0, 1, 1, 1, 0, 0. Subtract M from A and we'll get the result, which is again a negative. We restore A and set Q0 to 0. Step 3, shift left again. AQ becomes the result and subtract M. Again, we'll get a negative because it is 1, 1, 1, 1. Restore A and set Q0 to 0. Step 4, final shift. AQ is now 0, 1, 1, 0 and 0, 0, 0, 0, 0, 0, 4, 0. Subtract M and we'll get the result 0, 0, 1, 0, which is positive. Since the result is positive, we keep it and set Q0 to 1. And the final values quotient in Q is 0, 0, 0, 1, which is 1. And the remainder in A is 0, 0, 1, 0, which is 2. So the result of it is 1 remainder of 2. For the B part, the dividend is negative 5. So we use the 2's complements of 5, which is 1, 0, 1, 1. The divisor is 2 and the binary form is 0, 0, 1, 0. Its 2's complements for subtraction is 1, 1, 1, 0. A is initialized to 0, 0, 0, 0. For the first step, shift left, AQ becomes 0, 0, 0, 1, 0, 1, 1, 0. Subtract M and we'll get the result, which is a negative. We restore A and set Q0 to 0. Step 2, shift left. AQ is 0, 0, 1, 0, 1, 1, 0, 0. Then we subtract the M, we'll get 0, 0, 0, 0, which is a 0, which is a non-negative. So we keep it and set Q0 to 1. Shift left, AQ becomes 0, 0, 1, extra 0, 0, 1, 0, 0. Then we subtract M and we'll get 1, 1, 1, 1, which is a negative. Restore A and set Q0 to 0. Final shift, AQ becomes the result. Subtract M, then we'll get 4 zeros, which is a positive. So we keep it and set Q0 to 1. Quotient in Q 0, 1, 0, 1, which is 5. But since original dividend was a negative, we negate the quotient and get 1, 0, 1, 1, which is a negative 5. Remainder in A is 0, 0, 0, 1, which is 1. So we also negate the remainder to follow the rule 1, 1, 1, 1, which is negative 1. So the final result is negative 2, remainder negative 1. For question 4, let's do what the instruction asks us to. Load immediate 40. This instruction puts the number 40 straight into the accumulator. It just takes the value as it is, so it is 40. For B, load direct 20. The instruction refers directly to memory location, which is 20. When looking at the table, the data stored at address 20 is 50. So that is the value that is loaded into the accumulator. So the answer is 50. For C, load indirect 30. This instruction first checks what's stored in address 30. According to the table, address 30 holds 40. Now, we treat that as the new address and check what's inside the address. So the address 40 is 60, so the answer is 60. Load indirect 10. So first, the instruction reads the content of address 10, which is 50, then it uses 50 as an address and reads what's stored there. So address 50 contains the value of 80. So the answer is 80.